You know how AI is getting scarily powerful? Well, it's also getting unbelievably huge. So big, in fact, that the smartest AIs literally can't fit on our phones. So how in the world are we going to get this brilliant, massive brain onto a device that fits in our pocket? Well, it turns out the answer is hiding in a really strange, really beautiful field of math that kind of rewrites the rules of how numbers work. Let's dive in.
So here's the game plan for this explainer. We'll kick things off with what I'm calling the AI bloat problem. Then, we'll uncover this strange new math that, believe it or not, holds the solution. We're going to see how neural networks can be thought of as geometric shapes, how we can simplify their blueprint, and then we'll check out some really impressive test results before we zoom out for the big picture takeaway.
All right, so let's start with the main challenge. Why can't you just run the latest, greatest AI model on your phone or, your smartwatch?
Well, the simple answer is that these things are becoming absolutely monstrous. We are talking about models with billions of parameters that need a staggering amount of memory and just raw computing power.
And listen, this isn't just some tech nerd problem. It actually affects you directly. It means your apps feel slower because they have to phone home to a server somewhere in the cloud. That costs companies a ton of money. And, maybe the most important thing, it often means you have to send your personal data off your device, which, raises some pretty big privacy flags. We have to find a way to put these models on a serious AI diet.
That diet is a real thing. It's called model compression, or pruning. And there are basically two ways to do it. You've got unstructured pruning, which is kind of like trying to remove single grains of sugar from a cake after it's been baked. It's super precise, but it's a nightmare for the computer hardware to actually speed up. Then you have structured pruning. This is more like slicing off an entire layer of frosting. It's way more practical, way more efficient. And this is where our story really starts to get good.
To find a much smarter way to do this structured pruning, some researchers looked in a completely unexpected place. A pretty new field of math that, at first, seems like it has absolutely nothing to do with artificial intelligence.
So, welcome to the wild world of tropical geometry. It's this area of math that mashes up algebra and geometry by just changing the basic rules of arithmetic. It's seriously like learning to do math in a parallel universe. Okay, so how does this actually work? The rules are simple, but they will absolutely bend your brain. In this tropical world, when you add two numbers, you just take whichever one is bigger. So 3 plus 5 is just 5. And when you want to multiply two numbers, you just do regular addition. Yeah, I know. It's weird, it's totally counterintuitive, and it turns out to be the key to this whole thing.
So you're probably thinking, what on earth does this bizarre math have to do with shrinking AI models? Well, this right here is the big aha moment. What if an AI isn't just a tangle of code and numbers? What if it's something you can actually visualize? Something you can treat like a geometric blueprint that you can simplify? Okay, the bridge connecting these two worlds is a tiny, incredibly simple function that's at the heart of most modern AIs. It's called the ReLU activation function. All it does is take a number, and it spits out the maximum of that number and 0. Do you see that? The max operation? That's not just a coincidence. It is the exact same operation as addition in tropical math.
So here's the punchline. Because neural networks are just jam-packed with millions of these little ReLU functions, their entire mathematical structure can be described perfectly in the language of tropical math. The network's output is something called a tropical rational function.
And this image shows you exactly what that function looks like. See? It's not a smooth, gentle curve. It's a shape made of flat planes and sharp angles, all stitched together. This is the native language of tropical geometry. The AI literally is a geometric object.
And that object actually has a name. It's called a zonotope. The easiest way to think about a zonotope is that it is the literal geometric blueprint for a layer of a neural network. And once you have a blueprint, well, then you can start looking for ways to simplify it.
So this brings us to the actual tool, an algorithm called TropNNC. That stands for Tropical Neural Network Compression. It's designed to take that geometric blueprint and make it way smaller and much more efficient. TropNNC has this really elegant four-step process. First, it translates a network layer into its sonotope blueprint. Step 2, it uses a clustering algorithm to find parts of that blueprint that are basically redundant, the ones doing very similar jobs. Third, it merges each of those groups into one single, new piece that captures what they were all doing together. And finally, step 4, it rebuilds a much smaller, leaner neural network from that new, simplified blueprint.
And you can see the result right here. On the left, that's the geometric function of the original, big network. And on the right, That's the new compressed version from tropNNC. It's obviously much simpler, but you can see how it still captures the essential shape and the core behavior of the original. It's a pretty clever simplification.
Okay, so that all sounds fantastic in theory, but the real question, the one that really matters, is how well does this thing actually perform in the real world?
Now, before we even look at the numbers, tropNNC has this one killer advantage. It's a data-free method. It can shrink a network just by looking at its structure, at its blueprint. It doesn't need to see a single piece of training data. That is fantastic for speed, for cost, and of course for privacy.
Okay, so let's look at the data. This table compares tropNNC to an older geometric method on a classic image recognition test. Just look down the columns here. At every single level of compression, whether you keep half the network or just a tiny fraction, tropNNC holds a higher accuracy. I mean, check this out. Even when you've thrown out 95% of the original network, tropNNC is still humming along at over 97% accuracy. That's a full 2 percentage points better than the old way. In this world, that's a massive improvement.
And this bar chart really makes the story crystal clear. When you shrink the network by 90%, tropNNC doesn't just beat the old geometric method, it's even competitive with methods like thinit, which are data-driven. Now remember, thinit needs to see thousands of images to do its job. tropNNC needs 0. It's getting these top-tier results just by analyzing the geometry. That's incredible.
You know, the researchers themselves put it perfectly. They said their findings really do highlight the amazing and still mostly untapped potential of using tropical geometry to solve these really practical problems in AI.
Okay, so let's zoom all the way out and just quickly recap what this whole fascinating journey from AI to weird math and back again really means for us.
So let's wrap this up. We started with a really practical problem. AI models are just too fat to fit on our phones. The solution amazingly came from this abstract, kind of weird corner of mathematics, which gave us a brand new way to see AI, not as code, but as a geometric blueprint. That insight let an algorithm, tropNNC, intelligently slim them down, all without ever needing to see our personal data. And I think the biggest lesson here is that sometimes the most powerful breakthroughs come when you build a bridge between two ideas that nobody thought had anything in common.
It just makes you wonder, right? What other secrets are hiding out there in these strange worlds of abstract math, just waiting for the right person to connect them to the problems of tomorrow? What other blueprints are we only just now learning how to read?